Welcome back. This slice of physics is about geometric vector addition and subtraction. We're going to learn how to add vectors geometrically. We're going to take a look at what happens when we multiply a vector by a scalar, and we're going to learn how to subtract vectors. If I asked you what 1 plus 1 is, you will readily tell me that it's 2, of course. And that's true when we're dealing with scalars. When I'm dealing with vectors, the same is not true. If I have two vectors, A and B, and I add them, and let's say the magnitude of both is 1, the answer for A plus B can be 0, it can be 2, or it can be any number in between. How does that happen? Well, that's what we're going to take a look at now. So let's say I have vector A over here. There is A, and I have vector B over here. And I'm interested in figuring out what the sum of these two is when they are added as vectors. So I want to know what A plus B is. And let's call that result answer C. So we want to determine what C, which is the sum of A plus B, is. So in order to add them, there's a geometric technique we can use that's pretty handy. First, vectors are defined only by their magnitude and direction. So the length of the arrow, the magnitude, the pointing, which is the direction, those are the only two things that define the vector, not their location. So in this case, if I take A and I duplicate it over here, it's still A. Nothing has changed. And similarly, I can take B and duplicate it over here, and it's still B. Now the trick to adding vectors is to line up the tail of B against the tip of A. So vectors have tip, which is where the arrowhead is, and they have tail, which is the other end. And to add B to A, I want to grab the tail of B and move it to the tip of A so that they look like steps in a sequence. First I do A, then I do B. So here I have reproduced A, and I've moved B so that its tail is at the tip of A. And that's helpful because the answer for A plus B is then the original tail of the first vector to the final tip of the second vector. So this here would be A plus B, which is a vector. When I add two vectors, my answer is a vector, and in this case we chose to call it C. And just to be clear, these were vectors too. So you may be thinking, all that's fine, but how useful can this be? I don't have any numbers, I don't have any angles. We'll come to those later, but just this geometric addition sometimes helps us really set up and understand a problem clearly when we're dealing with velocities, acceleration, and coming up when we deal with things like forces. Now, while we're discussing addition, let's take a quick look at one more thing here. So if I put a vector in a coordinate system, it might look like this. So here's my vector, let's call it vector P. And when I broke it down into its components, I got Px over here and Py over here. Those were the projections of this vector along the coordinate axes. So I got Px and Py. Well, what is Px plus Py? When I add them as vectors, what happens? In order to do that, I got to drag Py so that its tail is on the tip of X. So I'll grab Py and move it over here so it'll look like this. And so Px plus Py would just be simply the original tail to the final tip, which reproduces my vector P. So Px plus Py simply is the original vector that we started with, which is why breaking a vector into components works, because when I add the components back, I get the original vector back. Okay, that's all we're going to discuss with regard to addition. Let's now discuss multiplying a vector by a scalar. Scalar is simply just a number, and vector has magnitude and direction. So if I have a vector A over here, and I want to find out what 2 times A is, what do you think is the answer? Well, your intuition really works well over here. It'll be a vector that's twice as long, in exactly the same direction. And if I multiply a by 1/2, you would expect a vector that's half as long in the same direction. And all of that is correct. That's how multiplying a vector by a scalar works. So one key thing here is that when I multiply a vector by a scalar, only the magnitude changes, not the direction. There's one caveat here. That's true as long as the scalar is a positive scalar. And we can further say that the length or the magnitude of the vector will grow if the scalar is greater than 1, and the length or magnitude of the vector will shrink if the scalar is less than 1. Now, if I take the same vector A and multiply it by -2, what do you think might happen? Well, let's just say what happens when I multiply it by -1, which is the same as -A. Again, your intuition probably will lead you in the right direction with this. All that happens is the direction of the vector reverses and the length remains the same. So this would be -A. And so -2A would be twice the length of A, but reversing a direction. And -1/2A would be half the length of A and a 180-degree rotation or a reverse in direction. Now all this is very useful when I need to subtract a vector from another. So now if I have vector r over here like that, and I want to subtract from it vector s, which looks like this, first I would simply reproduce r over here. Moving vectors does not change them. And then I will simply reverse the direction of s and make it -s. And then I will add that -s to r. So in order to add it, I move its tail to the tip of r. And then my answer would be the original tail to the final tip. So here's the answer for r minus s, which is also a vector. So let's call that vector t. You're familiar with the algebra trick where if I want to do x minus y, that's the same as x plus -y, which is the same trick we used here in subtracting vectors. We simply stated that vector r minus vector s is the same as vector r plus -s. And since we know that multiplying by -1 simply reverses the direction, and we already know how to do vector addition, we also now know how to do vector subtraction. Now, in case you're still wondering how all this is useful, let me give you a very quick example. Let's say I have a ball that's got an initial velocity in this direction. So that's my VI, and a final velocity. For whatever reason, the ball, after a little while, was moving in this direction. About the same magnitude because the lengths are shown as about the same, but the direction changed. Well, what's the direction of acceleration that caused this change in velocity? Well, we know that acceleration is nothing but change in velocity over time duration. And since time duration is a positive scalar, multiplying by 1 over delta t, which is also a positive scalar, does not change the direction. So the direction of acceleration is the same always as the direction of the change in velocity. And we know that the change in velocity is simply final velocity minus initial velocity. So if I want to get a sense of the direction of acceleration that caused this velocity change, all I got to do is subtract VI from VF, and that'll give me a direction of acceleration. So I can reproduce VF over here. I can take VI, flip it, and move its tail to the tip of VF, and I get my acceleration, or delta V really, is this vector, and the direction of acceleration is the same as delta V, so I don't know the length of the arrow it needs to be. That depends on delta t, but the direction of acceleration is going to be like that for this situation. So here are the 3 questions we set out to address in this slice of physics. How do we add vectors? We saw that you do that by moving the tail of one vector to the tip of the other and getting the sum as the original tail to the final tip. What happens when we multiply a vector by a scalar? Well, that depends on if it's a positive or negative scalar. If it's a positive scalar, the direction does not change. The length grows or shrinks based on if the scalar is bigger than 1 or smaller than 1. And if it's a negative scalar, pretty much the same thing happens except that the direction flips a 180. And finally, how do we subtract vectors? Well, we just add the -1 of the second vector to the first one. So a minus b in vectors is also a plus -b. Thanks for watching.